In this lesson, we will discuss one of our first inferential techniques, hypothesis testing. Researchers are studying the effect of a new dietary supplement on cognitive function. Participants in the study will take a cognitive test after a course of the new supplement, and researchers speculate that the participants will score higher than the standard mean score of 70. In a simple random sample of 100 participants who took the supplement, the mean score was 71.3 on the test, with a standard deviation of 16.4 points. Clearly, the sample mean score of 71.3 is higher than the standard mean of 70. However, we know that there is randomness involved when sampling that may affect the sample mean. Other factors such as the amount of spread present in the distribution and the size of the sample may also have an effect. So, the question is whether a sample mean score of 71.3 is far enough above the standard score of 70 to think that it is actually higher when all of the other factors are taken into account. The tool we use here is a hypothesis test. Now, in a hypothesis test, we start with a null hypothesis, which state what we assume the population parameter to be. In our example, we start off by assuming that the population mean is 70. The alternative hypothesis states the thing we believe to be true if the null hypothesis is rejected. In our example, the alternative hypothesis is that the population mean is greater than 70. Okay, let's think about the sampling distribution of the mean. If we knew the population standard deviation sigma, then we would know that the sampling distribution would have a mean that is the same as the population mean, which is 70, and the standard deviation would be sigma over the square root of m. It would then be an easy matter to look to see how far away x bar is from the assumed null mean. If x bar is too far away, we would determine that the difference we see is more than what we'd expect from chance alone, which in turn would lead us to think that the null hypothesis is not true. So you can see that would work out great if we knew sigma. Here though, we don't know sigma. The only measure of spread we have is s, the sample standard deviation. Turns out though that we can use s in place of sigma, but that will introduce a little more uncertainty to the process. And ultimately, what it means is that the sampling distribution is not quite normal anymore. Instead, it has a related one called the student's t-distribution. Okay, just a side note here. A young self-trained statistician named William Seeley Gossett was employed by the Guinness Brewing Company. During his time there, he developed what is now known as the Poisson distribution, and he used it to model the number of yeast cells in the beer-making process. Though his discovery was revolutionary and greatly improved the brewing process, he was prevented from publishing his results because his employers considered the information to be proprietary. He published them anyway, using the pseudonym Student, and that same Student made other discoveries in statistics, including the student's t-distribution. The student's t-distribution is very similar to the normal distribution, except that it has a little more thickness in the tails. What this extra thickness means is that the sample mean is just a little further out than it would have to be for a normal curve, which means that the evidence has to be slightly stronger before we reject the null hypothesis. The reasoning here is that because of the extra uncertainty in the process, we're just offsetting it by raising the bar a little. Okay, so we have the student's t-distribution with mean mu equals 70 and standard deviation s over the square root of m, which is 16.4 over the square root of 100, or 1.64. Now, take a look at where the sample mean of 71.3 is in this distribution. We see that it's not all that far from the hypothesized mean of 70, which shows that perhaps this value is just the result of chance. Had the sample mean been farther out in the tail of the distribution, we would have concluded that the difference was most likely due to something other than chance. Now, we need a way to measure this. Consider the area to the right of the sample mean. Let's think about what this area means. It's the probability of getting a value at least as extreme as the one that we got for the sample mean, under the assumption that the null hypothesis is true, which in this case is that the population mean is actually 70. In the case where the sample mean is 71.3, we find this probability to be 0.2149, which is not especially small. In other words, we would not call it an unusual event to see a sample mean of 71.3 when the sample was drawn from a population with mean 70. On the other hand, suppose that the sample mean had turned out to be something like 72.9. Here, we find the probability that we observe a sample mean at least as extreme as 72.9 to be 0.0385. Such a small probability indicates that it would be unusual to see a sample mean of 72.9 or more if we drew this from a population with a mean of 70. Having such a small probability would lead us to reject the null hypothesis and instead believe the alternative, that the population mean for those who took the dietary supplement is, in fact, greater than 70. Okay, so the probability of getting a sample mean at least as extreme as the one we observe, under the assumption that the null hypothesis is true, is called a p-value. We can think of the p-value as the probability that chance alone accounts for the difference between the sample mean observed and the hypothesized null mean. In general, the smaller the p-value, the less we believe the null hypothesis is true. Okay, there are a few things to unpack in this example. Here, we had an alternative hypothesis that stated that the population mean was greater than some value. We call this a right-tailed test. Sometimes we will have a left-tailed alternative, or even a two-tailed alternative. When the test is performed, the type of test just determines how the p-value is calculated. In this example, we had a large sample size, which meant that the central limit theorem for means kicks in. And even though we aren't exactly using the normal distribution, which is what's stated in the central limit theorem, we're using a closely related one. So we still need to make sure that the central limit theorem is turning away in the background. Now let's take a moment to consider the big picture of how hypothesis testing works. We start by coming up with a null and alternative hypothesis. Then, we check the assumptions to make sure that the test we are running is valid. Then, we run the test using the information we observe from the sample. Lastly, we interpret the p-value and use it to make a decision about whether to reject the null hypothesis or fail to reject it. Let's switch over to R for a moment. Generally, R assumes that you start with a set of actual data values, so there isn't a built-in R function for performing a t-test when given the summary statistics. That is, the sample mean, sample standard deviation, and so forth. However, I've written a function that will perform this test, and you're welcome to use it whenever you need it. The name of the function is onesamp t-test sum, which stands for one sample t-test given summary statistics. Don't worry too much about the code here, it's just computing the p-value based on the direction of the alternative hypothesis. Note, however, the inputs for the function. We have to know the sample mean, the sample standard deviation, sample size, and the hypothesized mean that's in the null hypothesis. There is also a direction option. Based on the alternative hypothesis, you should either enter less, greater, or two-sided. Let's run the test for the dietary supplement example. Here we have a sample mean of 71.3, a sample standard deviation of 16.4, and a sample size of 100. The hypothesized null mean is 70. In this example, the researchers speculate that the participants will score higher than the standard mean score of 70, so we know this is a right-tailed test. We enter greater for the direction. Let's enter all these into the function. Two values are returned. The first is what's called a test statistic. It tells how many standard deviations the sample mean is away from the null mean. The second is the p-value. Recall that the smaller this value is, the stronger the evidence against the null hypothesis. We find the p-value to be 0.2149. As stated before, this is not a very small p-value. Often, we will choose a tolerance level before performing the test that the p-value must be less than in order to reject the null hypothesis. This is called the significance level of the test and is denoted by alpha. A very common significance level is 0.05. Though if the test is something of extreme importance, it's not unusual to choose a smaller level, such as 0.01 or even 0.001. In this case, we fail to reject the null hypothesis at the alpha equals 0.05 level of significance. Because we don't reject the null hypothesis, there is reason to believe that it may be true. The mean of the population here may be 70. It sounds like the dietary supplement may not be doing what it's supposed to. Hopefully, you now see the way that hypothesis testing works. It's basically the same process when testing other types of parameters. However, it's important to know that each type of test comes with its own assumptions. These assumptions ensure that the p-value is being computed using an appropriate sampling distribution. As mentioned before, statistics can be tricky. Tests can be run and p-values can be obtained, but that doesn't mean that they are valid. Making sure that the assumptions are true before running the test will ensure that the conclusions you reach from the test are valid. The dietary supplement example was a hypothesis test for the mean. In this type of test, the assumptions are 1. We have a simple random sample, and 2. The sample size is large. That is, n is greater than 30, or it is reasonable to believe that the population is approximately normal. Okay, let's look at another example. A researcher is interested in knowing whether using a new type of LED light bulb will have an effect on the growth of a plant when compared to a traditional incandescent bulb. The average plant height with incandescent bulbs is 41.8 inches. In a sample of 21 plants grown with a new LED bulb, the heights were 34, 22, 20, 37, 72, 75, 68, 57, 42, 43, 59, 42, 34, 48, 56, 65, 51, 50, 62, 65, and 31. Is there evidence that the new bulb has an effect on growth? If so, what kind of effect? Okay, we have to be careful here. There are only 21 values in our sample, which is, of course, less than 30. So, the only way to proceed with the test is to verify that it is reasonable to assume that the population is approximately normal. Let's enter the data in R, and I'll call it plant heights. Let's take a look at the normal quantile plot. The data appear to mostly follow a straight line, maybe with a couple of minor exceptions. A quick look at the strip chart and histogram seem to confirm that the assumption of normality is reasonable. I think based on what we see, it appears that we should be okay moving forward with the test. Remember, if we hadn't verified the assumptions here, we could not have had any confidence in any results we obtained from the test. Okay, now I've modified the earlier program so that we can enter the data set as an input. The function name is oneSampTTestData. The inputs here are the sample data set, the null mean, and the direction of the test. We're told that the average growth height using incandescent bulbs is 41.8 inches. This is our null mean. Since we are looking to see whether the new bulb simply has an effect, that is, we don't know whether the height will be higher or lower, we're doing a two-tailed test. So let's run the oneSampTTestData function. First, let's note that the sample mean is 49.19 inches. Note also here that the p-value is 0.0464, which is fairly small. It indicates that if the actual height of the population of plants had remained 41.8 inches, we would get a sample with mean 49.19 only about 4.64% of the time. It seems more likely that the population mean height when using the new bulb has changed. Looking at the mean of the sample, it appears that the mean has increased. The previous two examples have been about testing a population mean. Now, we're going to consider a test for a population proportion. P-values for hypothesis tests about the proportion of a population are based on the normal distribution. However, as usual, there are assumptions that have to be satisfied in order to proceed. The assumptions are: we have a simple random sample. The population is fairly large, generally about 20 times as large as the sample. This assumption is to ensure that sampled items are independent of each other. The individuals in the population are divided into two categories. The values n times p0 and n times 1 minus p0 are both at least 10, where p0 is the hypothesized proportion from the null hypothesis. These assumptions essentially come from the central limit theorem for proportions. As before, if the assumptions are not satisfied, the results of the test are unreliable. Okay, let's jump into another example. A new vaccine for the prevention of infection by a certain pathogen is being tested. The previous vaccine had an effectiveness rate of 72.9%. That is, 27.1% of people who received the vaccine still got infected with the pathogen. In a trial phase, 480 people who are at risk of infection receive the new vaccine, and of those, 103 go on to be infected. Is there evidence to conclude that the new vaccine performs better than the previous one? Well, let's begin by setting up the null and alternative hypotheses, and then we'll check the assumptions for the test. With the previous vaccine, the proportion of people who received it that still got infected was 27.1%, or 0.271. We wish to see if this percentage goes down with the new vaccine. The null hypothesis is p equals 0.271 with an alternative hypothesis of p is less than 0.271. Let's go ahead and define x, the number of infected individuals with the new vaccine, and n, the sample size. Now we turn our attention to the assumptions. The first three assumptions are pretty straightforward. Let's now check the fourth assumption. The null proportion is p0 equals 0.271. So we find that n times p0 and n times 1 minus p0 are both at least 10, so we can move on with the test. Now, I've written another function that will perform the test given x, n, and p0 and the direction of the alternative. Let's plug these in and run the test. Okay, we find that the proportion of the sample is approximately 0.2146 or 21.46%. Is this enough of a difference to believe that the new vaccine reduces infections? Well, we see that the p-value is 0.0027. Such a small p-value provides very strong evidence against the null hypothesis. That is, we have strong evidence that the infection rate is indeed less than the previous rate of 27.1%. Let's look at one last example. A sample of animals is selected from a certain population. We want to test the hypothesis that at least 40% of the animals belong to the order Carnivora. We're going to import the taxonomy of the animal sample and take a quick look at it. Now we need to determine how many of the sample belong to order Carnivora. This is easily done by setting up a logical condition and then taking the sum. We call this value x. The sample size n can be found by computing the length of the sample. Here, the null hypothesis proportion is 0.4, and we go on to check the assumptions. We find that both n times p0 and n times 1 minus p0 are both at least 10, so we can proceed with the test. We run the oneSampProp_test function using greater as the direction. Here the p-value is 0.08. This is a fairly small p-value, which may suggest that we reject the null hypothesis, but it's not quite small enough to reject it at the alpha equals 0.05 level of significance. Our conclusion is that there isn't enough evidence to believe that the proportion of animals in the population belonging to the order Carnivora is at least 40%. I'm going to wrap up this lesson with a couple of points. Generally, when performing a hypothesis test, it is best to report the p-value, not just state whether the null hypothesis is rejected or not. The p-value allows others to decide for themselves whether the evidence is strong enough for the conclusion. The examples provided in this lesson demonstrate how to do a hypothesis test. However, performing the test is really only one phase of research. Just as important as the test is, making sure that the sample collected doesn't contain biases and is large enough, getting a feel for the data to know how to construct a meaningful null and alternative hypothesis, checking the assumptions to ensure that the results that you reach are valid, and understanding the results that you obtain from the test. One last point. The tests that we've run so far have either been based on the normal distribution or the closely related student's t-distribution. There are many other tests based on different types of distributions, some of which we'll look at in this class. All basically have the same framework. There are assumptions that have to be satisfied, a null and alternate hypothesis have to be constructed, the correct information has to be inputted into the test, and a p-value will be obtained which will allow you to make a conclusion. Alright, well that wraps up this lesson. Best of luck moving forward.